Okay, here we go. Kinesiology 230. This is chapter 17, talking plyometric and speed training for these next presentations. There's 10 of them. And out of these 10, you have a couple sidebar presentations that I put in. Just my thoughts on speed, agility, quickness, how to develop speed and teach speed, and some of the drills, etc., that kind of layer back into what they're talking about in the book. But without further ado, let's get going. Now we're going to be starting off on page 447 here in the book, and they go right into the things we're looking at, the mechanics and physiology of plyometric and speed enhancement. And believe me when I tell you, you can do an entire class on plyometrics, an entire class on speed enhancement, because plyometrics are not just inherent to one part of the body, lower body. You can do upper body, lower body rotational activities as well. And keeping with a theme, and just kind of keep this in your head as we're talking through this chapter. We're talking very much about a transferability of skill from one thing to another. And with the book itself, they have main headers in the book. These are the main headers in the chapter itself, if I can say it correctly. And we're just going to go right through top to bottom. So starting off with plyometric mechanics and physiology. That by definition, a plyometric movement is a quick, powerful movement consisting of an eccentric action, or it's a counter movement, which equates to a pre-stretch, and that's followed by an immediate, powerful, concentric muscle action. Now, I urge you to try to just think this through in terms of one muscle to start, or think of it in terms of, instead of eccentric and concentric, you may have to think of it in terms of negative phase and positive phase, because when we go into a eccentric movement pattern, the eccentric movement pattern can have eccentric and concentric parts to it. So, for example, on a box jump, when you drop down to your quarter squat position to get ready to jump up on the box, that counter movement itself and that pre-stretch, though in essence you're eccentric loading the muscles that are going to be performing the jump itself, you can have some concentric action in there. So it's a little bit of a brain bender, and I've said it before when you get into multi-joint exercises, but it's especially a brain bender when we start getting into plyometric movements. Plyometrics and speed, they both rely on a stretch shortening cycle, and we talked about that before. It's kind of like we did a brief introduction to that before. We were talking about muscle spindles and GTO, but you're talking about the cycle of shortening a muscle to be able to, elongating a muscle to be able to shorten it quickly, meaning eccentric loading to concentric loading. Now, plyometric exercises, they use that stretch reflex that we just talked about or just brought up, and the natural elastic components of muscles and tendons to increase power production. It is partially musculature, it's partially neurological, and it's partially the tension that's actually in the system itself. Anytime we start talking about plyometrics, we start talking about a component of time. And the time component, we don't actually sit there with a stopwatch and determine just how long it takes a person to do a counter movement and jump, or when their feet leave the ground to landing on a box. But because the counter movement, the eccentric phase, the concentric phase, is very short in terms of the transition between those two, it becomes very power oriented. And your body has to be trained to be able to handle those forces that are involved. And the two main models that they use to describe the production of this muscular power are the mechanical side and the neurophysiological side. If we were to just kind of look at them side by side, the mechanical model is about the elastic energy that's stored after a rapid stretch, like a rubber band, and then released during concentric actions. We have this pre-stretch that happens when we do the eccentric loading. There's an amortization phase where it's a quick pause, and then boom, we have a quick contraction, then we jump on the box. So the three main models that we have in the musculotendinous side of the equation: series components, parallel elastic components, and contractile components. And these are things that will be familiar to you once we get into them here in this lecture. The neurophysiological side relies on the stretch reflex, and it's the involuntary response of the body to react to the rapid stretch. I'm just reading it right from the slide there for you. But this rapid stretch sends a signal to the spinal cord. And remember, when you have a signal being sent to the spinal cord, it's afferent in nature. Remember, you put the hand on a hot stove and the signal goes up the peripheral to the central nervous system to say, hey, dummy, take your hand off the stove. And then there's a signal back that's sent back down on the contractile side that pulls your hand off the hot stove. Well, when we talk about the neurophysiological side of doing a box jump, we drop down to our quarter squat, we get ready to jump. there's a stretch reflex there where there's an impulse sent up the central nervous system that states to the brain. It actually doesn't really make to the brain, it goes across the thoracolumbar region, but it goes on the sensory side stating, hey, we're being stretched. That's the afferent side. And the signal that comes back down is rapid and quick, and it's a contractile response to contract the overstretched muscle. So the stretch reflex, it responds differently to different rates of stretch. So if you do a slower counter movement, that stretch reflex is going to be different than a quick counter movement. The reflexive component of plyometric exercise is composed of the muscle spindle, right, if you remember that from a couple lectures ago. And the strength of the response can increase with training. So on the right-hand side, when we look at this, the faster a muscle is stretched, the greater the concentric force after the stretch. So you pull that rubber band back, you have a lot of potential energy stored up, you let it go, it's going to have more kinetic energy. If you do that faster with your muscles, you're going to end up having a greater power output. So you have greater potentiation with the short stretch shortening cycle. And what they get after in the book here is they talk about potentiation is the increase in force output following a previous activation. And this is due to the neural side. And you'll hear this and read this in literature all the time. We talk about muscle activation and potentiation, and you're trying to think of this in terms of what is potentiation. And it's the ability to have a muscle or the entire motor unit itself, because there's a myoneural component to this, because there's a neural side of it, be able to fire rapidly after a stretched event. And this diagram to the right looks like a big hot mess, but if we really just kind of look at it, and I just want to keep it simple, you have CC, that's the contractile component, that's this guy right here. The series elastic component is right here. And then the PEC, which is the parallel elastic component, is right here. So when the person is standing, this is what you have in the standing resting model. The counter movement, when they drop down, you'll end up having a rapid stretch. And in that rapid stretch, in the mechanical model, you'll have the way the contractile component works is you have an eccentric phase. And you'll notice this represents the actual muscle fibers themselves at the sarcomere level, where you have the Z's. Remember, the Z's get pulled towards the M during muscle contraction, but during eccentric loading, the Z's are actually pulled further away from the M. And that's what you see here, is that you have the Z and the Z, and the M would be in the middle of it. They still have it represented here. No movement, stays the same. This is commonly referred to, this in-between time, as the amortization phase. It's the pause, the fraction of a second when you go from the counter movement to the jump, when you go from the eccentric loading to the concentric loading. And you'll notice what happens here is when we go ahead and actually go into the jump up, you have the stretch shortening cycle happens, where you have the series elastic components in the muscles contract, and it brings the myofibrils, the actin and myosin interact with each other, and you have the Z's are brought closer to the M. Excuse me. And now on the bottom here, this neurophysiological model, if you overlay these two, kind of think of them working concurrent to one another. Here you have the stretch shortening cycle. There's a signal. The muscle spindles detect a rapid stretch and send a signal to the spinal cord. And then the spinal cord, this is the thoracolumbar region I was mentioning before, where that signal doesn't even go up to the brain. To save time, it goes just right across the spinal cord in the thoracolumbar region. It goes to the spinal cord, it hits the synapses, a signal is sent back to the muscle during the amortization phase. And then you have a motor signal that's sent down to the muscles, and that causes the reflexive muscle activity. What I want to point out is this is just one agonist, one prime mover, if you will, that's being represented here. Probably we're talking quadriceps, just giving the resting position, the counter movement, and then the jumping movement that you see here in terms of knee flexion to knee extension, and just the muscles, how they work in knee flexion and knee extension. You're looking primarily at the quadricep. But in this process of going from resting, counter movement, pause to jump, there is a whole series of muscles that all work together to make that happen. We could be talking about gastroc and soleus. We could be talking about the hamstrings on the antagonistic side, right? So this is probably one of the easiest ways to wrap yourselves around both the mechanical model and the neurophysiological model, and have an understanding of the main processes that happen when we have a plyometric movement. stretch shortening, eccentric phase, amortization phase, concentric phase. Just kind of wrap yourself around that and give it a big old hug. All right, moving on. Which is stretch shortening cycle. The eccentric phase, that's the deceleration phase, and it involves preloading the agonist muscle or muscle groups. During that phase, the SCC, let me go back to this. The SCC is your series elastic components. Those are in the muscles. They store elastic energy, and the muscle spindles are stimulated. You may recall that the muscle spindles actually lie or in line fiber-wise with the muscle fibers. I would ask you to just kind of commit this to memory because you're going to see it somewhere else. In the stretch shortening cycle, they talk about eccentric, amortization, and concentric. Eccentric, you're stretching of the agonist muscle, and they talk about the physiological event here. Amortization phase, this is a pause between 1 and 2. They talk about what happens here. And this is another thing I would ask you to maybe take a few moments just to pause me and commit this to memory and get an understanding of how like eccentric and concentric and amortization all work together in terms of the mechanics of working on plyometric work. So I'm going to jump out of this. I'm going to move on to the next presentation. I got a ton more to cover. Moving on.